Welcome back, focused learners. I'm your host, and today we're tackling an absolute beast of a topic that practically dominates chemistry exams. We are talking about the D and F block elements. Now think of me as your personal, enthusiastic study mentor for this session. We're going to take these seemingly complex transition metals and completely demystify them. Because by the end of this explainer, you aren't just going to be memorizing facts, you're actually going to understand the underlying logic, which honestly makes acing those tricky exam questions so much easier. Let's get right into it.
Here is our game plan for today's high-yield review. We're starting with mapping the blocks, then the IUPAC rule, the microscopic engine, the cascade effect, the F-block showdown, and wrapping it all up with a fast review and cheat sheet.
All right, Section 1, Mapping the Metal Blocks. Think of the periodic table like a massive architectural blueprint for all matter. Right there, sitting dead in the middle, you've got the D block. It acts as this central bridge connecting the S block on the left over to the P block on the right. Now, this specific block contains the absolute structural backbone of human civilization. We're talking elements like iron, copper, and titanium. But if you look down below that, disconnected and kind of sitting at the bottom all by itself is the F block. These are the inner transition metals, or as we affectionately call it, the basement. This is the wild frontier of nuclear energy, housing heavy hitters like uranium and thorium. Just keep this mental map in your head because it tells you exactly how these electron orbitals actually fill up.
Moving smoothly along to Section 2, the IUPAC transition rule. So, according to the strict IUPAC definition, a true transition metal absolutely must have an incomplete D subshell in either its neutral atom or its common ion. If you're taking notes right now, literally circle, highlight, and underline that word incomplete. That is the single most crucial keyword you need to memorize here. Because that incomplete shell, it's the engine. It's the source of all the active chemistry, and it's exactly what allows these metals to do all the incredibly fascinating things they do.
And of course, because it's chemistry, there are exceptions. Enter the Group 12 imposters: zinc, cadmium, and mercury. You will almost certainly be tested on these guys. So why aren't they considered transition metals? Well, because they possess completely full D subshells in both their ground state and their common oxidation states. It's best to think of their electrons like money locked away inside a heavy bank vault. The vault is closed super tight, so those D electrons simply do not participate in bonding. Because their shells are already full, they are officially kicked out of the transition metal club.
Okay, Section 3, the microscopic engine. For the 3D series, electrons usually fill up nice and sequentially as you move from left to right, but exams love to test you on the outliers, and here are the two you absolutely have to know: chromium and copper. At chromium, that's element 24, an electron spontaneously shifts from the 4s orbital into the 3d orbital. Now, why on earth would it do that? To achieve the unique symmetrical stability of a perfectly half-filled D subshell. So instead of the predicted 4s2, 3d4, it actually becomes 4s1, 3d5. And the exact same trick happens at copper, element 29. An electron shifts to achieve ultimate stability, but this time through a completely filled 3d subshell, making it 4s1, 3d10. The energy gap between 4s and 3d is just so incredibly small that the atom naturally reconfigures itself to find that perfect symmetry.
Which brings us to Section 4, the cascade effect properties. What's really interesting here is how that incomplete shell causes a massive chain reaction of testable, real-world properties. First up, hardness and melting point. Transition metals are notoriously tough. And it all comes back to, you guessed it, the incomplete shell and its unpaired d electrons. Think of those unpaired electrons as a really strong covalent glue between the atoms. The greater the number of unpaired valence electrons you have, the stronger that interatomic interaction becomes. That's exactly why metals, right in the middle of the series, where they have the absolute most unpaired electrons, boast the highest enthalpies of atomization. Their metallic bonds are just exceptionally strong. Next, we have what I like to call the chameleon states, which is their ability to show multiple different oxidation states. Because the 3d and 4s energy levels are sitting so close together, these atoms can lose multiple electrons sequentially. The visual pattern here is super helpful. The oxidation states basically form a pyramid, peaking perfectly right in the middle with manganese. Manganese can actually utilize all of its 3d and 4s electrons, reaching states all the way up to +7. Oh, and here's a massive pro tip for your exam, called the flipped rule. Unlike the P block, where lower oxidation states get more stable as you go down, heavier D block elements actually favor higher oxidation states. For instance, chromium 6 is highly reactive, but molybdenum-6 and tungsten-6 are highly stable.
Now for my favorite cascade properties, color and magnetism. When transition metal ions are sitting in a solution, their d orbitals actually split into different energy levels. Electrons in those incomplete orbitals then absorb very specific wavelengths of light to jump between these newly split levels. The light that isn't absorbed, that passes right through, and that's what gives the solution a brilliant, vibrant color. Keep in mind, empty or completely full orbitals are strictly colorless. And those unpaired electrons we just talked about, they act like tiny little magnets. They align with external fields to generate paramagnetism. More unpaired electrons directly equals a stronger magnetic pole, which you can actually calculate using a simple formula where n is the number of unpaired electrons.
Let's keep this momentum going into Section 5, the F-block showdown.
So let's head down into the basement of the periodic table to compare the inner transition elements. We've got the lanthanoids filling the 4f orbitals and the actinoids filling the 5f orbitals. The absolute defining difference between them is just how deep these orbitals are buried inside the atom. You see, the 4f orbitals of the lanthanoids are buried so incredibly deep that they barely affect outer chemical bonding at all. But the 5f orbitals of the actinoids protrude a lot further out. This means they participate heavily in bonding, making their chemistry wildly complex by comparison. If there is one high-yield tool you memorize for your exam, make it this comparison. Lanthanoids are highly predictable. They're very similar to each other. They're dominated by a super stable +3 oxidation state. They are mostly non-radioactive, and their magnetic behavior makes sense. Actinoids, on the other hand, are the total rebels. Because those 5f electrons protrude and participate in bonding, their oxidation states are all over the place, hitting +7 just like manganese. On top of that, 100% of actinoids are radioactive, and their magnetic properties are incredibly complex and irregular. They are two wildly different families living in the exact same basement. And you know, we really can't talk about the F-block without covering this key exam concept, the Lanthanoid Contraction. Imagine the nucleus is a powerful magnet pulling everything inward, and the inner electrons are like an umbrella trying to shield the outer electrons from that strong pull. Well, it turns out those diffuse 4f electrons make for a really terrible umbrella. They provide remarkably poor shielding. Because of this, the growing positive charge of the nucleus effortlessly pulls the entire electron cloud sharply inward. This contraction has a massive, highly testable consequence. Elements in the second and third transition series, like zirconium and hafnium, end up having nearly identical atomic radii. That makes them incredibly difficult to separate in a lab setting.
All right, we made it to Section 6. Let's do our review and hit that cheat sheet.
Let's just ground all this pure chemistry theory into reality for a second. Everything we just learned isn't just for passing a test. This is the actual orbital geometry that builds our modern world. Those strong covalent bonds from unpaired electrons, that is exactly what gives us the supreme durability of structural steel. The easily changing oxidation states, that makes metals like platinum and palladium the ultimate chemical catalysts used in cars and factories globally. The unique locked vault properties of zinc and cadmium, they quite literally form the energy grid of modern rechargeable batteries. And those protruding 5f actinoid electrons, that precise chemical instability yields the massive quantities of nuclear energy that could realistically power our future.
Okay, here is your rapid-fire cheat sheet. If you're going to pause this explainer to take a screenshot, this is the one to grab. Just remember, every single anomaly, every single weird trick these metals do is a direct cascade effect of that one core trait, the incomplete electron shell. Unpaired electrons give you hardness and high melting points. Close energy levels give you those multiple oxidation states. Split orbital energies result in vibrant colors in solution. Spin alignment gives you paramagnetism. Do not forget your group 12 imposters with their locked vaults, zinc, cadmium, and mercury. And remember that the terrible shielding of the 4f subshell causes the famous lanthanoid contraction.
It's honestly pretty wild when you think about it. All this immense power and chemical utility actually comes from an imperfection. It comes from an incomplete shell. Which leaves us with his final thought. If every incredible property of these transition metals, from structural steel to vibrant paints to nuclear energy, stems exactly from what they are missing, how might we further manipulate these incomplete shells to build the unimaginable technologies of tomorrow? Keep that in the back of your mind as you go ace your exams. Thanks so much for joining me on this Explainer Focus, learners. Keep studying hard, and I'll catch you in the next one.